All right, let's go back just for a moment and revisit some rules we do in series circuits. What are three things we know about series circuits?
Current is the same throughout the circuit.
Yep.
The sum of the voltage drops equal the total source voltage.
That's right. Say that again one more time. Whoever said that? Something?
He said the voltage drops if it's, add up to the total voltage.
Oh. And RT is equal to R1 plus R2 plus R last, whatever that might be. So those are three hard, steady rules that always apply in a series circuit. We add all the resistances, we get R total. Anywhere in that circuit, I is going to be the same value. Any point we interrupt that circuit and measure current, we're going to measure the same current. And the voltage drops of each resistor when totaled equals source voltage, or VS, V sub S, which is an abbreviation of V sub, V source, or V total, it can be VT. But basically whatever the applied voltage is. Now,
Hey,
Number 5 is bull.
sir,
Number 5 is bull.
moving right along. I sense disdain and disharmony. So now we're going to go to parallel, and those rules are going to change. There's still going to be some rules. They're just going to be different. And we're going to find that out as we go along. How did we go about that? Yeah. Oh, flat, go back to it. In New York minute. Tomorrow we'll talk about it. I want everybody throughout all. Yes. Not that y'all would call each other and go, hey, I figured out that number 10. Well, yeah, that's, there are some, and then there are some that are on the other end of the spectrum. Don't feel bad, I don't know names everybody.
I'm Christian.
Me, Christian? I'm sure. Who said that? That's his name.
That's my name. Well, I'm a son. I'll tell my family, hey, I'm Christian, and I'll be taking.
Look at it,
Yeah, I want to let I can't talk. That's funny.
Well, I'm Marcel.
Okay. All right, let's go back parallel. See, I'm losing the class already.
That don't play long.
I'm telling you. All right, wakey wakey. Here's where it gets fun. Most circuits are actually combinational circuits. We're going to be getting the series parallel, but let's just take time to get through parallel before we worry about the series parallel. It's a circuit that provides more than one path between any 2 points. And when we look at this schematic right here, it's easy to see, if I don't press the wrong button, that I've got a source and I've got a path through R1. And remember, a circuit is a path from positive, negative, negative to positive, depending on which way you choose to pick the current flow. If I'm going from negative to positive, I can go through R1 and return to the source, or I can go through R2 and return to the source. And remember, these little lines here is a symbol for ground, and it's indicating that all these points are tied to our negative. So get used to seeing that, because that's what you're going to see on a lot of schematics, but it's essentially the same as drawing that line right there. So on this parallel circuit, I've got the ability to go through R1 back to my source, through R2 back to my source, and through R3 back to my source. So I've got more than one way. Previously in a series circuit, there was only one way to and fro, and that was because that is the very nature of a series. There's only one path. But parallel, if we think about something in parallel with something else, it pretty much defines that we've got more than one path. And you can see it here. If we label this positive and this negative, you know, we've got a schematic of one resistor going from negative to positive, the next resistor going from negative to positive, the next going back to positive, and the next. So if we drew that schematic, it would be identical to this one, except there would just be one more resistor out here. And it would look something like that. And again, that's why we have schematics. It just gives us the ability. I mean, I can look at that and readily see I got 4 resistors in parallel. I've got to study that a little more to kind of understand that and break it down. But if you look, the bottom of this resistor is at the same point as all the bottoms of these. The top of this resistor is at the same point as the top of all these. So they're really all in parallel with each other. All right, now, current, this is where it changed. Remember, current in a series circuit is the same at any point. In a parallel circuit, it's going to differ in each branch. So if we go back here, I've got a current path through R1, I've got a current path through R2. The only place I'm going to have total current is heading away from the source or heading back to the source before or after the split is done. So if I'm leaving here, I've got full current at this point, but when I get to this junction, part of my current is going to go through R1, the other part's going to go through R2, and they're going to rejoin after the junction again. So if we use red for total current, green for R1's current, blue for R2's current, then it would look something like that. We'd start out with total current, green part of it would go this way, part of it would go that way. But just for the sake of argument, let's say this total current is 3 amps. Green is 1 amp. Then what would blue have to be? 2 amps. So we just realized the law just based on a preliminary understanding, and that's the sum of the branch currents are equal to the sum of the total current. So if I take each individual branch, so in this one it's just these 2 branches, but here it would be this branch. Let me erase my add-on here. It would be this branch plus this branch plus this branch equals total current. So the sum of your branch currents equals total current. So we found out there's a way for a different path for current in parallel. So again, we add those branch currents to get total current. But what do you think in a parallel circuit if these 2 resistor values were the same and I had 6 amps of current? What do you think is going to happen in each branch? 3 amps. So some of the similarities, at least, are a little familiar. But yeah, if we're applying 6 amps and we have similar loads in each branch, we can divide that by the number of branches we got and go there. Same would hold true here. If these were all, if the applied current here was 9 amps, what have I got going through if all the R1, R2, and R3 were equal? 3 amps, same thing. So again, we can start seeing some things that we can, understand about parallel circuits through that. So sum of the branch currents is equal to the applied total current. The voltage across each component is equal. And again, we're talking about simple parallel circuits. Bless you. I've got this voltage source on this one. I'm applying some amount of voltage here. Let's follow the path. The bottom of R1 is connected to the negative. The top of R1 is connected to the positive. R1 is seeing the entire amount of Vs, whatever that might be. If it's 5 volts, 10 volts, 15 volts. R1 has a drop of whatever Vs is. But if I carry on, this is still the same point. Right here and right here. R2 is seeing the same voltage source that R1 is. They're both electrically connected. And it's really easy to see on this board, if this is Vs, and this is my negative, here's all my negative terminals right here. Here's all my positive terminals right here. It's easy to see that I'm applying the same voltage, or dropping the same voltage across each of those resistors. So, let's go back to that rule. Oops. Okay, here we go. Voltage across each component is equal. Current through each branch is determined by the source voltage and the resistance of the branch, and we're about to get there. So, this is just what we talked about. We have a 2K and a 2K, and again, what does those ground line mean? They're connected to the same point, right? So I'm going to draw this for you a few times, and after a little while, we're just going to have to get used to seeing it as it sits. But what is the voltage drop of R1? What's the voltage drop of R1? Oh. It's whatever we read across it. What would we read across R1?
10 volts.
10 volts. What is the voltage drop across R2? 10 volts. Whatever we would read across it. Now, we've got a 2K and a 2K, and this is telling us we've got 5 milliamps coming through here and 5 milliamps coming through here. And that gives us a total of 10 milliamps, right? By at least what's on here. Now here's where it gets fun. If I've got 10 volts and 10 milliamps, what is my resistance total? 10 volts, 10 milliamps, 1 what? 1 K ohm, because it's in milli. So what we just said was RT equals 1 K ohm. Now you're thinking to yourself, but wait a minute, 2K and 2K is 4. Resistors are supposed to add. They do in series circuits. They don't in parallel. If they're equal, we can kind of say the divide. But we're fixing to show you a formula here in a minute that shows you exactly what happened. But if they're equal, if I had 10 2Ks, I could literally divide 2K by 10 there. But if they were mixed values, we're going to see that change a little bit. 2K in parallel with 2K is 1K. And we'll get to that formula. Just stay tuned. But the important thing is to remember the current through this branch and the current through this branch equals total current. Total power is the power through each. So this is adding the branch currents, power through each resistor in the branch to get total power. That's the only commonality I think we have between the series and the parallel. We do add the powers. All right, so I'm fixing to show you There's the resistance formula. Well, this is series and parallel. This is a nice chart. This is a good comparison. All right, so let's talk about series first.
They're both in series.
They are. Shame on Painter Boydell. There we go. We fixed that, by golly. Y'all do that on your screen now. Y'all really impressed. Oh, wait a minute now.
You said so.
Somebody's gonna break out the Sharpie here in a minute, and I'm gonna regret ever saying that. Don't do that on your screen. All right, let's talk about what it's saying here. In a series, our source voltage is equal to our voltage drops across each resistor. All that's saying is, we add the drop of R1 to the drop of R2, we should get source voltage. In parallel, R1 and R2's source voltage are equal to the voltage source. And that's because we've got the same path. Positive goes to R1 and R2, negative goes to R1 and R2. And that's why it's equal in a series, is because when we come here, crap, don't touch the board. When we come here and measure with a voltmeter, right there, we're measuring across both of them, and we're getting the total. And that's exactly what's happening in parallel, is we're getting here and here, and this is the same point electrically as this. So we're always going to measure source voltage across the parallel branch, or the applied voltage, in a simple parallel. So that's where they're different. We have to add them in series. We just take the source voltage, and that's what's being applied in parallel. Current, IT, is the same anywhere in the circuit. I can break that circuit anywhere I wanted to and put in a current meter, and we're going to measure the exact current anywhere in that circuit. Over here, we've got to take the current through branch 1 and add it to the current through branch 2 to get total current. Here's the formula you've been waiting on. Well, actually it don't. It's just kind of a nifty. We're fixing to still get to it. RT, we add these together. Over here, we have to do a formula saying they're in parallel. I'll go ahead and quickly give you that formula. 1 over R, the screen is uncalibrated again. That's why I keep writing lopsided. 1 over RT equals 1 over R1 plus 1 over R2, dot, 1 over R last, whatever the last one would be. There could be 100 in there. We'd have to do 1 over R2, 1 plus 1 over R2 plus 1 over R3 plus 1 over R4, all the way up to 100.
Is that reciprocal together?
Yep. So let's go back for a minute. We had 2 2Ks a while ago, and we came up with 1K as the answer, right? So let's see if that works out. 1 over RT. Again, I've got to calibrate this board. I'll do it while y'all got a break here in a minute. 1 over RT equals 1 over 2 plus 1 over 2. Okay? 1 over RT equals, what's 1/2 plus 1/2? 1, right? It's it'll be 2 over 2, which is really 1, but we'll go ahead and show the full. In the interest of those who like math, that really becomes 1 over RT equals 1. And if we reciprocate both sides, reciprocal of 1 over RT is RT, the reciprocal of 1 is 1. So RT does indeed equal 1. So, and again, it's always going to be lower than your lowest. It may be significantly lower, it might be minutely lower, but it will always be lower than your lowest.
The power stays the same.
Power stays the same. We have to add the powers of each resistor drop two together to get the total power of the circuit. All right, we're not gonna go and conduct it, but that's a good one to leave up there while you guys get a break. So let's take a break. We'll be back about 10 after. Who's that kid?
I think it's just one day. It's Thursday. It's March 2nd, 2017. I just remembered when I got an email telling me, reminding me of I got a few more months before we go vacation.
Cause I know it's up on.
Yeah.
I saw you.
Outdoor travel.
Yes.
And
You can actually get ahead too, if you know.
can I say okay, good.
Did you say we weren't gonna be doing
I was
this?
hoping
We
if
won't
nobody
do
had
it,
touched
no.
our coolers since like.
I have managed to make 33 years in
My
electronics.
coworker back there?
The only time I remember doing conducting is when I was in college,
A little bit.
especially industrial electronics.
Yeah, she was coming in while.
And again, I'll tell you guys, the same way I tell my students, if you hit a job that conducting becomes a part of your everyday life, I truly believe, I'm not being sarcastic. I wanna know, what use is that?
But you would show me.
Dang, you really on me. Aren't you?
Yeah, we can work with you ahead of time, if you remind me of a bus, we might have, if not, you can always catch
I
up.
just
and get
got
back.
the email last night and I thought about it. I said, Lord, I got to see it.
Callie did not stop. All right, so we talked about conductance, but again, conductance is just one of those things I've never encountered in 33 years of electronics. It's the exact reciprocal of resistance. So if you're ever asked for conductance, get the total resistance reciprocated. There you go.
Is your conductance and series circuits as well? I know we never.
Yeah,
it never
it's the same.
came up.
Yeah, so you just invert the resistance and you got conductance. All right.
That's the formula.
Let's calculate the formula. Now we have two formulas for parallel resistance. We have the one I showed you before, which is 1 over R2 equals 1 over R1 plus 1 over R2 plus, and then dot, 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 all the way out to R last. This is also another one, but it only works with two. So if we take, and we say, for instance, while ago, that was 2 times 2 over 2 plus 2. What's 2 times 2?
4.
What is 2 plus 2?
4.
What does that equal to?
4.
1. And this was all in K, so I'll go ahead and say 1K on. So that formula works if you have just a mere 2 resistors. If you have more than 2 resistors, you have to do it with the first 2, get that value, and then do it with the next one. So I'll give you an example of that. Let's say we have a circuit, and I did not calibrate this board, I forgot. So we'll give everybody a moment to get back in anyway. I'll go ahead. Wow, this thing loses calibration.
No guilt.
Really? This early?
Guilt.
This a hot sound?
I eat a piece of chicken. It's early in the morning, I'm
That is on YouTube forever, ladies and gentlemen.
You gonna put me on YouTube, Friday?
Okay, I'm gonna go back. We learned R1 times R2 over R1 plus R2. And I'm gonna show you that's why this will only work with 2 resistors and not a third, or how you would do it if you had a third here. And we'll see that both formulas work. But if I have a circuit, that's much better. There's R1. Here's R2. Here's R3. We'll just is my total resistance gonna be less than?
One.
1 ohm. If we don't get less than 1 ohm when we do this calculation, we know we've done something wrong, because we know that total resistance will be less than the lowest branch value of what we're calculating. So let's do the 1 over RT first. So 1 over RT equals 1 over R1, which is 1, right? Plus 1 over 2 plus 1 over 3. So that formula is 1 over R1, R2, and R3, and they just happen to be 1, 2, and 3 respectively here. So now we've got to do our common denominators, right? I can't add those fractions. What's my common denominator? 6. 1 over RT equals 6 over 6 plus 3 over 6 plus 2 over 6. 1 over RT equals 11 over 6, right? Now, we know we can reciprocate both sides at this point, so we can come out here and write RT over 1 equals 6 over 11. RT over 1 is really equal to RT. What is 6 divided by 11?
1.1. Oh, no.
0.5454.
So it's repeating. 0.54 ohms. Well, 0.54 ohms is indeed less than 1, so we are potentially correct. Now, if we do the R1 times R2 over R1 plus R2, we have to do them 2 at a time. So I'm going to do R1 and R2 first. And we're going to get an equivalent value of those 2 in parallel. So if we say 1 times 2 over 2 plus 1, that gives us 2/3, which is really 0.67, right? So the equivalent of R1 in parallel with R2 is 0.67 ohms, and I'm going to write R1 parallel with R2. So what I've got now is a parallel equivalent of these 2, and now I can take that parallel equivalent and do the same thing with R3. So I can take 0.67 times 3 over 0.67 plus 3. Well, what is 0.67 times 3? I know. All intents and purposes, it should be 2. Yeah, it's going to be 2 basically if we carry that decimal place on out. But if we go 2 point, what was it? 0.
2.01.
We'll go ahead and write it. Because what we're doing is we're rounding. We're going to have a little bit of a rounding factor here. And what is 3 plus 0.67?
3.67.
All right, so let's do the math there. Yeah.
0.54.
5.4 what?
5476.
And this was 0.545454, wasn't it? So really, if we round it off to 2, we would come up with 0.55 here. And if we round this one off, we're going to come up with 0.55 here. So because of the way the rounding went, we really didn't get much of a, we got no difference at all. But we arrived at the same value. So we know both formulas are workable. It's just that we have 2 steps here, and you're thinking, here's what every student thinks. And I'm going to show you why it doesn't work. And this is wrong, that's why I'm going to write it red. They think, well, can't I just multiply 1 times 2 plus times 3 and then divide it by 1 plus 2 plus 3? Why can't I just plug that in? Let's try it. 1 times 2 times 3 over 1 plus 2 plus 3. What is 1 times 2 times 3? What is 1 plus 2 plus 3? If we do it that way, RT equals doing that product over sum formula, we can only do two at a time. Always.
That's where you got me.
If we do product over sum, we've got to do them two at a time. We can't do across the board.
That's where you got me.
Now, if you got a calculator, this, in my humble opinion, this and a couple of bucks will buy you a cup of coffee. Or $4 if you're going to get that Ariana Grande. At Starbucks. But, your calculator has the ability to do a reciprocal. The Windows calculator and most of your personal calculators that you have here too can do the same thing. So, remember, the formula is reciprocal of R1 plus the reciprocal of R2 plus the reciprocal of R3. But I gotta plug it in. So I'm gonna say R1 is 1, right? So I'm gonna say 1 reciprocal plus 2 reciprocal plus 3 reciprocal. And I've gotta hit equals or I had to perform the final calculation, right? So I'm gonna hit equals, and then I take the reciprocal of that, and I've got my across the board value there. And I can do it pretty much in one fell swoop. So let's work another one. Let's change the values from something other than 1, 2, and 3, because I don't want to confuse you with R1 being R1 and R2 being so forth and so on. So let's do that. You're confused? Well, let's unconfuse you. All right, we know that parallel branches, RT is always going to be less than the largest one, right?
Yeah.
All right, so let's make up some stranger values here. Excuse me, lower than the lowest. All right, so let's do a 6 ohm. Let's do a 10 ohm. Let's do a 30 ohm. So what is our resistance total going to be less than? It's got to be, or we have mathed incorrectly. So we can do, let's start with product over sum. We did the one over a while ago. So let's start with product over sum. Again, we have to solve them two at a time. So I'm going to go ahead and solve and get the sum of the parallel branch of R1 and R2. And this is R1, this is R2, this is R3. So I'm going to get these two. This will be R1 parallel with R2. So we're going to say 6 product over sum, right? 6 times 10 over 6 plus 10. And actually, I'm going to write the answer instead of writing the equation. So it's product over sum. So we multiply the two, we add the two, and we do the math. So 6 times 10 is 60. 6 plus 10 is 16. That gives us what? 3.75 ohms. So we know that to be at least potentially true because we paralleled a 6 and a 10, and it had to come out less than 6, and it did. So when we parallel this 3.75 and this 30, what's it got to come out lower than? 3.75. So this is equal to R1 parallel with R2. So now we're fixing to do this R1 and parallel to R2 value with the 30 ohm. So we're going to say 3.75 times 30 over 3.75 plus 30. What's 3.75 times 30? 112? 112.5. And I can do this one. Don't even need a calculator. Famous last words. All right, somebody do that math for me.
I got 3.3.
Got what?
3.33.
No, this is the product over sum formula. Yeah, we're going to do the reciprocal in a moment. what we did here, and there are two different formulas, I know this can be confusing. If we're doing the product over sum, it only works with two resistors. We have three here, so we gotta do the first two, get the equivalent, and then take that equivalent value and do it with the last one. So we did two different product over sum. We did it with the first two to get its equivalent value of R1 in parallel with R2, and then we took R1 in parallel with R2's value and paralleled it with R3, and because its value was 3.75, we knew we had to come out with something less than 3.75. So we got 3.3333333. So that works. We know that at least all the way through our math seemingly worked. Now we can take and do the same formula with, I'm just slam out of room, because I'm going to insert another page. It's 6, 10, and 30. So we're going to say 1 over RT equals 1 over 6 plus 1 over 10 plus 1 over 30. Now we don't have to do them two at a time here. We can do them all in one fell swoop. But we got to get a common denominator. 30. So what would 1/6 be? 5 over 30 plus 3 over 30 plus 1 over 30, right? That equals what? 9 over 30. So we've got 1 over RT equals 9 over 30. We can reciprocate each side, and RT equals 30 divided by 9. RT equals 3.33. So we arrived at the same answer. Now, it's a two-step process, seemingly, no matter how we do, or fairly seemingly complex. Because we've got to do two at a time here, and then do the third, or we got to come up with this same common denominator mess that we don't like necessarily doing. Or if you love math, you might enjoy it. But we can also do it with a calculator. And I'm going to actually do this formula with a calculator. I'm going to say 6 reciprocal plus 10 reciprocal plus 30 reciprocal. Now I hadn't totaled it until it had equal. And now I've got 1 over RT, and if I want RT, I just reciprocate it. That's a whole lot better than having to write it out on paper, in my humble opinion.
Oh, man.
But if you're out in the shop floor, it's good to know this other way, because we don't have calculators everywhere. Oh, wait a minute, never mind. So when I'm using my calculator, I'm doing the reciprocal form. I'm just entering it into my calculator. I add the reciprocals, I total it, and I reciprocate that, and boom, I've got the reciprocal. I've got the RT, I should say.
Lord, thank you for the calculator.
So, we see that either formula works, we just got to remember some rules. And let's go back and we'll prove the other way that all my students like to get confused about on the other end. They say, well, I should just be able to do product over sum and multiply, add across the, multiply across the top and add across the bottom. 6 times 10 times 30 over 6 plus 10 plus 30. That's 60 times 3 is 180. That'd be 1,800 over 46. Somebody math that for me. Nowhere near. Nowhere near the right answer. So, and of course, we would know that if we always remember it's got to be less than our lowest, and our lowest was 6, and so certainly 39. But if you ever get mixed up and use this, 9 times out of 10, it won't work mathematically if you'll remember that one law.
Is either way better than the other one?
That,
So you can use either one.
right. And one thing I should point out is back here, and we'll erase it, I didn't have to do the first two and then the third. I could have done the last two and then the first. It really wouldn't have mattered. It's gonna work out the same way mathematically. I can choose these two, and I can get R2 in parallel with R3 is equal to, product over sum, 10 times 30 over 10 plus 30. And that's gonna be 300 over 40, and that's gonna equal what? 7.5. Is that right?
Yes.
So 7.5 ohm. Well, the rules still apply. We had a 10 and we had a 30, had to be less than 10. If 7.5 is less than 10, so the parallel equivalent of R2 and R3 is 7.5. Now I can do product over sum of that one. I can do R1 in parallel with R2 in parallel with R3 is equal to 6 times 7.5 over 6 plus 7.5. What is 6 times 7.5? 45. 45 divided by 13.5. 3.33 repeating. So I write the same answer, I just work the opposite way. So if I do product over sum, it doesn't matter if I go left to right or right to left, I just gotta do two at a time, I can't do all three. But that reciprocal and your calculator works for me pretty good.
I wish you could show me where a reciprocal button on this calculator was. I can't
It's
see it.
probably x to the negative 1.
Above 7.
X to the negative 1. So like 9 x to the negative 1 is 1/9. I don't know why they took away the 1 over x. I hate them for
So
it.
it's x to negative 1.
Right.
Is my reciprocal.
So if we just did what up here on the thing, 10 and 30. So if we say 6 x to the 1 plus 10 x to the 1 plus 30 x to the 1 equals x to the 1 10 over 3. If you hit it one more time, I think you get it right. Oh, that makes perfect sense. But anyway, there's your reciprocal. And there's my little fish. Let's think about something for a minute. And when we think about it, it really applies. In our homes, the more we plug in, are we drawing, if we're turning more and more things on, plugging more and more things in, are we drawing more current or less current? More current. And what's inversely proportional to current? Resistance. If we're going up in current, we have to be going down in resistance. Just like that metal bar across your car battery. You pop a metal car across your car battery, you got infinite current and almost zero resistance until something blows up. So as in parallel, which is the way our homes are wired, the more we plug in, the lower our resistance goes. And that's why resistances in parallel, instead of going up, go down, because we're increasing current. So that's one way to think of it. Now, if we do have the same value resistor, we really already hit upon this, we can divide that by however many we have and get that the easy way without having to go through. But we could do reciprocal of 5.1 plus reciprocal of 5.1 plus reciprocal of 5.1 equals, and the reciprocal of that, and we'd come up with 1.7. It would work mathematically if we perform those calculations. So you don't have to remember this rule. You can just choose to do the math. We can do the product over sum of two of them, and then do the value of that with the third, and we get the same thing.
So that works the same thing as
It does, as far as what?
like what we were just covering.
Yeah.
It's the same thing?
If they're the same value.
Oh, I got you,
Yeah, if I've got three of the same value, I can take that one value and divide it by three, and I'll get the overall. But let's pop out the calculator just for grins and giggles. I won't map it out on the long way, but I'll show you with the calculator that it does work. So I'm gonna take 5.1, I'm gonna reciprocate it. 5.1 reciprocal plus 5.1 reciprocal plus 5.1 reciprocal equals reciprocal 1.7. So that is a shortcut if they all happen to be the same value, but we don't have to even remember that. We can just go back and apply our normal method, and we're gonna arrive at the same answer. So this is just a shortcut method. So if I had 10 5.1 Ks all in parallel, I would divide 5.1 by 10, and my overall resistance would be what?
0.51.
0.51 or 510 ohms. Be 5100 divided by 10, or 510 ohms, or 0.51. Depending on how we want to express it. So, we've got the choice. Kirchhoff's current law, bah humbug, rock and roll.
Everybody, oh, hold up, first off, that's easy.
What's that?
Kirchhoff's, current law.
Well, it's easy in the expression,
Right.
it's not so easy in the
In the math.
equations. Right.
Oh, okay, I got you.
But the algebraic sum of the currents entering and leaving a point must equal 0. All that's, so don't worry about Kirchhoff.
Oh, okay.
Because we get into nodes, it's a different way of knowing what we already know. And we're not going to talk about current sources, we're not going to talk about current dividers. All right, let's do talk about an open branch, though, because this changes everything. This is where we need to have an understanding when we're troubleshooting. The voltage across the open is unchanged. This may be the last time I draw the line for you. But I'm going to draw that line back. So we got R1 in parallel with R2, right? They're both seeing 10 volts. If one of those opens, in this case R2, if I measure across R1, what am I going to measure? 10 volts. I'm going to go right back to my source, and I'm measuring source voltage. If R2 opens, what am I going to measure? 10 volts. And the reason for that is I'm going right back to my source. Now R2 is no longer in parallel with R1. The remnants of the connections are, but R2 is no longer there. So what has happened when R2 opens is we've gone back to a simple series circuit. Resistance just went from whatever the lower value was between having the two resistors there to just R1's value. So current just did what? Dropped or rose? Dropped, exactly. If we had a heater plugged in and we had a light bulb plugged in and the heater kicked the fuse or we unplugged it, then all we got was the light bulb. Current just dropped. Keep going the wrong way, my hand. Dropped. Even if the light bulb went out, even though it doesn't draw as much as a heater, it still dropped proportional to where it was. So yeah, we just changed the dynamics of this circuit, and this circuit just went from a parallel to a series. In this case of this circuit, now if we had 3 or more resistors, it's still a series, but our overall values still change because we dropped the resistor. But we're still going to measure 10 volts across that broken resistor, but we're also still going to measure 10 volts here. If we can get back to the source, we're going to measure source voltage. And I've got a path here to the source, but even though this guy is broken, I've got a path here to the positive, a path here to the negative, so I'm still going to read source voltage. So if I got a motor that's bit to dust, internally, I'm still gonna read source voltage there. All right. Shorted branch. This is where it gets really fun. I'm gonna erase my handiwork here. If we have a short across a branch here, so we talked about that glob of solder. So I drop, you know, I got these leads on the back of here. Here's my lead coming out of this guy on the back side of this board, and here's my lead here. And something happens and I drop something that shorts those two out. What I've basically done is I have just shorted R1. What happened to R2?
Nope.
Nope.
No current. Because there's no resistance that's drawing all the current.
It shorts R2 too.
Okay.
If this is A and this is B, there's a direct path to A and B. Well, what is different here? This electrically is A, this electrically is B. If I'm shorting here to here, I'm also shorting here. Current takes the path of least resistance. All my current's gonna flow here, nothing's gonna flow over there, because I've got a dead short path. And what's gonna happen there is either lots and lots and lots of smoke, or a circuit breaker or a fuse is gonna trip. Hopefully the latter not forming. So, and that's why we have circuit protection. If my radio in my car suddenly shorts out inside of my car, it's gonna try to draw maximum current out of that battery, but I've got a fuse in there and that fuse is gonna go poof, and my car is gonna keep running. I'm just not gonna be jamming anymore. But if I didn't have it protected, infinite current's gonna try to draw through that radio until car catches on fire, the wires to the radio burn in two, or my battery gives up the ghost. Probably my radio wire, after mounds of smoke poured out of it, would eventually burn to a crisp and just open it up. But chances are my car would catch on fire too. So that's why we have fuses. So if we have an open branch, we talked about that, we're gonna read source. Shorted branch, circuit resistance is gonna drop very close to zero. Current is gonna instantly go up, full max. And if the circuit is fused, which it needs to be, it's gonna open. And if it's not, either the shorted component or the source is gonna burn open. Something's gonna keep happening until something gives up the ghost, for lack of a better term. We're not gonna get into the current sources, we'll talk about that potentially some other time. Yeah, not that. And again, we already talked about the common connection, so get used to seeing this and get used to drawing that line for yourself. And they may not always be even. They may be in a circuit, but understand if you see this symbol, that means they're all electrically connected together to ground. We'll talk about floating commons probably at some other point. We'll kind of leave it out for this particular point. That's it. So what questions do we have on parallel circuits at this point?
Can you play with some?
Sir?
Can you play with some?
Yep. On the board. Let's take a break. We'll come back at 5 till, and we'll probably work some problems on the next step.
I figured it was.
Let's see if that's next. Oh, actually, the assessor's next, but I think we'll work some problems. Gotta work.
Finally figured out where you got me.
Yeah, it kind of felt that.
No, they ain't that not a thing. Find some of these red bottles. Still smell.
What's the deal with these apple bottles? It's winter, like $200.
Hey, well, I still smell like pineapple.
Oh, apple bottles? I ain't paying for that. Just when you have apple.
Find some vanilla. Some balloons smell like vanilla.
Tell me about that. Some already got too good. That's one valve, that's valve just talking about 399. And for men, that's why you ain't well.
Like some really short man or something, look at them souls.
Now they are my life. That little night. And see, it's a well.
You like clothes and shoes. You got to stand there and stuff.
No, I ain't with no stuff, I'm just on this website. I tried to flip.
Like my son, I told him he bought another darn tennis shoe and called me and tell me he like Bill do. I choke him.
I got a pair. I should've put them on there, like $200 from Jordan. That just came out.
So wrong with you.
That's all the kids, well.
I don't know, you know,
You ain't no
you know, you look in the mirror.
Oh, good, you ain't no
I'm
kid.
sorry.
Look, my kids don't wear them.
Gone.
If they knew, I
I
didn't buy
like
them.
Jordan shoes.
See, look at these pictures.
I like Jordan too, but that's damn expensive for me. I ain't
Maybe
paying
for you.
$200 for
They don't
that
like to
sneaker.
play that.
That's
That's
what
the Jordan retired.
Shannon, I go cut out me some
No.
apple bottom and put it on the back of my
Y'all got
pants.
both
I know,
best
I know.
shoes still.
Oh, I know.
Apple bottom
We'll-
jeans.
we'll-
They're crazy. Ain't no way in the world.
Well, I don't
I
know.
love y'all,
Uh-huh.
Yeah, it is.
Yeah,
a
but
solid.
look at her.
Their jeans too, they're very expensive.
Say what?
They been out.
Yeah, that's what I'm
What?
saying, apple bottom jeans.
Apple bottom.
I ain't paying.
That's about like my mom,
That's
my
it.
sister. About like my mom,
Them
my sister
energy.
getting in that argument about whether they not they bell bottom. About her pants are bell bottom. My mom like they bell bottom. My sister like, no, they ain't, they flares. They're bell bottoms. It's like they flares.
Darn, my friend must be sitting at her desk.
I wore those
Texas
and
record
they
so
go,
quick.
they bell
The
bottoms.
new mall.
Yep, the new chocolate chip thing there.
It be too big for me. It's too many people over there. Good
Where,
God. It stay
yeah,
big.
man.
At the rivers.
Yes. I still like those hood. No, they ain't got no air conditioning there no more.
When?
The old mall?
Oh, mall, I don't even believe they got air conditioning.
Mm-mm.
What?
Every
They
spring
take all
holiday.
winter, they're hot.
It might.
I ain't going
Yeah.
there anyway.
Yeah, you better go at daytime.
You got raw.
Don't go there with no hood, no car. It's getting tough.
Really?
Seriously.
They say that's one of the highest crime rates in Macon is at that old mall.
Wow.
Go to the west side.
Ain't nothing in there to go look for anyway.
Mm.
We need to be in there for
You
anyway.
know, they got the hood right down the road in Parliament. Go to Columbus on Victory Drive.
I know one dude.
Hoover to the
I,
outlaws
My friend
in Columbus.
took me
Real quick. That's
He had
why
just-
I'm better
he had
than
just
Lowe's
quit, but-
Road.
Yeah.
And there's one cat, he went I was still up in South Carolina. He went out in Charleston around Northwoods Mall. Dude thought he was gonna rob him.
I ain't grabbed
That was a bad idea. He tried to rob an ex-Marine. Dude had just got out the Marines too, man. He turned around, took the gun from the dude and beat him in the face until he couldn't pick his arm up. The dude had to have his, when they took him to the hospital before they took him to jail, had to have his jaw wired shut.
Maybe y'all ain't been telling no lies, y'all been, well, did y'all wanna work some problems, or did y'all wanna go ahead and assess?
Yes, let's work some problems.
Where's the problem?
All right, let's have a little fun. Let's apply some rules, let's talk about what we've learned thus far. And we'll just start out with some very simple circuits here. All right, we've got a 50-volt source got R1, we've got R2, and this
We got
is
D two.
10 ohms, this is 20 ohms. So let's see what all we can find. First of all, we can find the V of R1, we can find the V of R2, we can find I of R1, we can find I of R2, and we can find RT total, and we can find the IT total, not necessarily in that order. And we'll even get into some power here a little bit later. All right, so let's start with the easy stuff. What is the V of R1? 50 volts. What is the V of R2? 50 volts. Just remember, in a parallel branch, the parallel branches are seeing the same value. What's the next thing we could potentially solve for? Yeah, we can go ahead and get I of R1. All right, what is the formula for I? So 50 volts divided by 10 ohms, 5 amps, right? So what we've got, we still don't know total, we know this. We know we've got 5 amps here. The total's got to be more than 5 amps. We've got some value here, 5 goes this way, some other value goes that way. So it's going to have to be more. All right. What about of R2? What is I of R2? 2.5. So let's see how we calculated that. We've got 50 volts again, divided by 20 ohms. That equals what? 2.5 amps. All right. So I'll write 2.5 here. So what is I total? 7.5 amps. Now we did that by adding this to this and getting that, right? We're going to find out after we get our R total, we can still use Ohm's law and we should arrive at that same value. So let's do R total. Do y'all want to do product over sum? Or we'll do both. We'll be like the little kid on the commercial. Let's have both. All right, so let's do 10 times 20 over 10 plus 20. That'll be 200 over 30, which will equal 6.67 ohms if I'm mathing in my head here.
That's correct.
All right? Or is it the 60? No. It's 60. Sorry. I second guess myself. You should never do that. All right. So does that work? Is 6.67 less than our lowest one?
Yes.
So we don't know if we're right. We just don't know that we're absolutely wrong. So now if we want to see if we did do it right, just like he said, we can take 50 volts divided by 6.67 ohms, and we should arrive at this IC that I forgot to put amps on. I put ohms up there. Man, y'all shouldn't have given me a break. Y'all got to retrain me now.
I know you're wrong.
All right. Smartboard wasn't so smart then, or at least the operator is smartboard. So it is 50 divided by 6.67 equals 7.5.
7.67.
All right. So we feel pretty good that we solved it. We did product over sum over here. Let's do reciprocal. We'll do the long-handed. Whoops. We did the long-handed reciprocal a while ago. 1 over RT equals 1 over 10 plus 1 over 20. Common denominator? 20. 1 over RT equals 2 over 20 plus 1 over 20. 1 over RT equals 3 over 20. We reciprocate both sides. RT equals 20 over 3, and if we do the math, what do we come out with?
This is,
0.67. All right. So there you go. So no matter how you slice it, and we can do that with our calculator if we wanted to. We can say, what was it, 10 and 20? 10 reciprocal plus 20 reciprocal equals reciprocal 6.66667. So the math works no matter how we do it. All right. Is that fun or what?
oh, yeah,
Or
well,
what?
All right, so let's we modify some things. I'm gonna try to keep this up here.
Yeah.
I showed it. You'll probably show me again here in a minute. At least one I showed it. Famous last words right there. Now, let's get rid of these. Let's do this. Pull it this way. I'm gonna add in R1 equals R2 equals,
No, you got RT.
that should be 2. Thank you. I was contemplating the next move and not worried about the first one. So we're gonna say this is 10 ohms. This is R1. I will keep it simple one more.
Those still 50?
Yeah, let's change that. Let's go 120. Now this one's gonna be 500 ohms. So, yeah.
You've already given us all from the constitution.
Well, I'm just gonna kind of leave it so we can fill it in. This will apply no matter what what your givens are. So yeah, we could actually go ahead and populate those if we want to. And this is what I do when I'm working problems with my guys is I'll go ahead and that's one of the things they teach us, go ahead and pre-populate your norms. So now, we did it a little different a while ago. We actually went ahead and solved, we did our V's and we did our I's and then we did it the other way. But we can go ahead and solve RT right now, can't we? RT, R total, 10 times 500 over 10 plus 500 equals 5,000 divided by 510.
9.8.
How much?
9.8.
9.8. Is there another decimal or does it work out even?
It's 9.803.
Okay, 9.8 works good then. All right, so we've already got R total, R total. So we can get I total, somebody said it. So what is our applied voltage? Divided by our R total, 12.24 what? So what we do know is we've got starting here and coming back here, if we were to insert an ammeter at any point, we would get 12.24 amps. And we know the sum of the two branches has got to equal to that 12.24 amps. So let's do IR1 now. So how do we get the value of IR1?
Volts
Alright, so 120 volts over a resistance of 10 ohms, right?
Yes.
That equals how many amps?
12 amps.
12 amps. So we know right here, we've got 12 amps of current. I can guess what's going through that other one. Anybody guess? 124. So I'm gonna go ahead and write it, and we're gonna prove it Ohm's law wise. Before we do, so let's take Ohm's law. I never did write R1, did I? So it's 12 amps. And we'll go ahead and try Ohm's law. So what is our voltage? What is our resistance?
500.
Equals what? Wow. 0.24 amps. We'll go ahead and plug it in. So we proved that part. And the last part's about the simplest thing we got up here. What is V of R1 and R2? 128. So let's go back to our rules. And let's see if this circuit makes sense from a parallel standpoint. Parallel branch, we'll see the applied voltage. V of R1 is 120, V of R2 is 120. That's true. Resistances in parallel are going to lower, and they're going to be lower than the lowest. We got a 10 and a 500. We calculated RT to be 9.8. That seems to hold true. The sum of the current through the branches equals total current. So we got 12.24, 12 goes this way, 0.24 goes this way, and when they meet back up, we have 12.24. So that also holds true. So it works. So, let's throw another one in here. I'll try to write just a hair smaller. I'm gonna make this one a little more interesting. 100 volts. So R1, R2, R3, R4. 1 ohm, 10 ohm, 100 ohm, and 1,000 ohm or 1K ohm.
You put 1,000 on the third one.
I did. Man, I just got 0 happy. Thank goodness it wasn't this. All right, so we got 1, a 10, a 100, and a 1,000. So let's go ahead and write down some things we want. We're gonna want VT, V total, which we know already. We wanna know V of R1, V of R2, V of R3, V of R4. Let me write a little smaller. We're gonna need a little more room. V of R1, V of R2, V of R3, V of R4, I of R1, I of R2, I of R3, I of R4, R total, I total. Bless you. So, what do we want to get first? Let's fill in our knowns. What is V total? What is the V of R1? R2, R3, R4? 100. And the only reason I write these is it's a good way of referring back. We really know that, and I don't have to put them all down. But when we start doing these formulas and we're trying to refer back to our I's and our R's and our B's. It just comes in handy, in that respect. So what can we calculate next? There's a couple of different ways we can go here. Y'all wanna do current first, or y'all wanna do resistance first? Current, I heard current, all right? So, we'll do current of R1. I of R1 is equal to what? 100 volts, right? Divided by what? 1 ohm. So IR1 equals what? 100 what? Amps. So R1 equals 100 amps. Pulling a pretty good load there. All right, let's do R2. I of R2 equals to 100 volts, right? Divided by how many ohms? 10 ohms. So I of R2 equals what? 10 amps. IR3 is equal to 100. Probably starting to see a pattern here.
Yep. That's gonna be one.
Divided by 100 ohms. R3 equals how many amps? 1 amp. Yep, and R4 will be 0.1. I'll do it in black. R4 equals 100 volts divided by 1,000 ohms equals 0.1 amps, or 100 milliamps. We'll keep it in amps. So what is our total current? Yep, 111.1. If what we said holds true, we can add the 100 plus the 10 plus the 1 plus the 0.1, and IT should be 111.1 amps. So now, let's do RT. Which formula do you want to use, or do you want to use a calculator? All right, we'll do a calculator, and we'll go back. We'll do the reciprocal formula on line 2, because I want you to see that it works. So it's 1, 10, 100, 1,000. All right, so don't forget, after you get your total, you gotta hit your equals. That's the gotcha of using this calculator. So we're gonna say 1 reciprocal plus 10 reciprocal plus 100 reciprocal plus 1,000 equals, and when I get the reciprocal of this, it should be less than what? Less than what?
Yeah.
One is a reciprocal on 1,000.
Is it really? 1 reciprocal plus 10 reciprocal plus 100 reciprocal plus 1,000 reciprocal. Now, it should be less than what when once I reciprocate it? It should be less than 1. So I'm going to take the reciprocal of that. There, less than 1. So RT is equal to 0.900 ohms, or just not 0.9. Now let's see if that works out ohms law-wise. We had 100 volts divided by 111.1 amps. I got the calculator up here. 100 divided by 111.1 equals 0.9. And Bob's your own. Dog my cat. Ray Porter would say. Whatever that means. Ray says it quite often. So let's see if that works if we math it. 1 over reciprocal equals 1 over 1 plus 1 over 10 plus 1 over 100 plus 1 over 1,000. What is my common denominator? 1,000. That would be 1,000 over 1,000 plus 100 over 1,000 plus 10 over 1,000 plus 1 over 1,000. 1 over RT equals 1,111 over 1,000. We reciprocate it, RT equals to 1,000 divided by 1,111. Well, by golly,
You got it.
who did yours think? I'm trying to think of one. I don't want to give you one of them impossible problems like I did the other day. Y'all enjoyed that, I know, though. Let's see if I can erase some of this. So if I were to be sly, and I would give you, whoops, I erased some of these values. Now here's where your calculator isn't your friend, but let's do this. Let's give you RT. Give you RT of 5 ohms. Okay? Make sure I don't screw this up royally. Not me. So R1. Our total is 5 ohms. This one is 50 ohms. This one is 25 ohms. And this one is 10 ohms. And this one is our unknown. And that's all I'm gonna give you.
What about one?
That's the one you got to figure out.
Voltage is still the same.
Voltage is still the same. So how are we gonna find R1 if we've only got R2, R3, R4, and R total?
Figure everything.
And I pray this works. 1 over RT, excuse me, it's not 1 over RT, is it? It's 1 over what? What is RT? Right. 1 over 5, because we've given RT a value of 5, correct? Equals 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. So we're trying to solve for R1. So I need to take away, I need to get R1 over to the left side, right? Well, we can do this. Minus 1 over R1. And we can subtract minus 1 over R1 here, right? Okay. I gotta subtract it to get it over here. 1 over R1 minus 1 over R1. Is that right?
You got to move it to the other side, so you have to add it to the other side.
Hey, you gotta add it to one side.
Do the opposite to the other side.
No,
Yeah.
Find the common denominator against those three.
Yeah, what he said.
I trust
Understand
you.
the common denominator.
All you gotta do is find the common denominator between those three and then subtract it
Yeah.
from the 1/5.
All right, yeah, all that doesn't even matter. Where we were going would work, he's absolutely right. He is absolutely right. Let's go ahead and find the common denominator. 1/5 equals 1 over R1 plus, he applied the much simpler version. What's our common denominator?
50,
So this is what?
5, 50.
Very good. All right, 1/5 equals 1 over R1 plus 8 over 50, right? So now, let's get a common denominator over here. What's the common denominator between 1/5 and 8 over 50? 50. So this becomes 10 over 50 equals 1 over R1 plus 8 over 50. So now, exactly what he said, what do I need to do?
Now you could subtract.
850 is from both sides, right? So if I say minus 8 over 50, minus 8 over 50, we'll have to come over here, and I run a slide by the room. 2 over 50 equals 1 over R1. Reciprocate that, 50 over 2 equals R1. R1 equals 25 ohm. Didn't have it. I wrote it right here. So that's 25 ohms. So let's see if the math works. If we go back and actually take that new value and plug it in, we should be able to go back to our original formula and get it, right? And we won't cheat and use a calculator. We'll actually do it. We'll remove our total, which we already know, we have it written. But we've got this, I'll take away this question mark here and I'll write it on the correct side. Kind of parallel everything else. So we're saying 1 over our total equals 1 over 25 plus 1 over 10 plus 1 over 25 plus 1 over 50. Common denominator, 50. 1 over RT equals 2 over 50 plus 5 over 50 plus 2 over 50 plus 1 over 50. 1 over RT equals 7, 9, 10 over 50. We can reciprocate. RT equals 50 over 10. RT equals 5 ohms. And by golly, that's, thank you. Because I was carrying us down a much harder big path, what you should. That's right. All right, so let's go ahead and get the rest of this stuff. We know that we not only found it by doing that, but it appears to be correct by applying the original formula. And let's do everything else. Let's go ahead and solve this equation. All right, what is V total? 100 volts. And again, you don't have to write all these down. I do it because it helps me when I refer to all these equations. But so is V3, so is V4. Now, we can take two different approaches. We can find individual branch currents, and then we can add those and get the total, or we can take 100 and divide it by 5 and get I total. So what is I total? 20 amps. It's 100 volts. I total equals 100 volts over 5 ohms equals 20 amps. So when we get these individual branch currents now, they should add up to 20 amps. So let's see if it happens. So let's do the I of R1. That would be I equals V 100 over 25, right? So what is IR one? 4 amps, right? All right, let's do IR two.
And our group is the same thing.
Yep. We got the same values. R2 is 10 ohms, 100 volts divided by 10 ohms. R2 is what? 10 amps. So this is actually ends up being the exact same thing for R3, right? R3, since they're the same value, equals 100 volts divided by 25 ohms, which equals 4 amps. Then last but not least, IR4, 100 volts divided by 25 ohms,
About
50 ohms. Wake up, Lee. Equals 2 amps, right? So if we add, let's populate these things, 4, 10, 4, 2 amps. So, 4 plus 10 is 14, plus 4 is 18, plus 2.
Why you got a whole?
Oh, I was looking at it like that.
Say something.
Oh my
Say something. But yeah, these 4 should add up to total current. And if I go back and make this guy blue, which is what I meant to do, I'll show you exactly what's happening live in living color here. What is literally happening is we've got 20 amps chugging along right here. And let's see, we use this. When we get here, half of that current is splitting this way. So that means we've got 10 amps going this way. How many amps are left going that way?
4 amps going that way, right?
Well, I got the wrong one. Yeah, I do. Thank you. Sorry. I looked at R2 instead of R1. Shame on me. So we've got 4 amps here, right? So I got 20 to start with. I got 4 left. What if I put a meter right here, an ammeter right there? What am I going to measure? 16. That's exactly right. Because I had 20, 4 branched off. I've got 16 here. And we hadn't really talked about that, so I'm glad we encountered that. All right, so 4 goes that way. When we get right here, what's coming down this branch? R2. 2 amps, right? We got 4 amps down this branch, 2 down this one. What?
You got 10.
Well, this is R2.
You got 10 amps.
Oh,
It's all over 2.
Christ. Thank y'all. People out in the video world, sorry. And all y'all too. I'm going crossways is what's happening, I guess. Alright, so IR2 is 10 amps. So, right here we said we had 16, right? 10 just went away. If I were to put an ammeter right there, what would I have? 6. And that adds up because my last 2 are 4 and 2. So, same thing happens. When I get to R3, I'm going to try to hold myself to task here. R3 has 4 amps, right? And this last one has 2 amps, right? I'll use red again. They need 5 colors when I'm doing these. So, it all depends on where we break this circuit as to what we read. If I were to insert, let's play ammeter insertion here. If I inserted an ammeter right there, what am I going to read? 20 amps, because got 20 amps coming, it splits. 2 amps combined with 4 amps right here, that 6 amps combines with the 10 amps right here, and then that 16 combines with the 4, giving us 20. So yeah, we would read 16 amps there. What if I inserted an ammeter right there?
Read 6, 12.
Yeah.
You get 4.
You got
6
that,
amps.
you got
6
4 and
amps.
2 on both sides.
I'm gonna read the branch current coming through R4 and the branch current coming through R3, and I'm gonna read 6. Now, I'm still lacking 14 because I hadn't combined my last 2 branches going back this way. What questions do y'all have besides can your instructor label? Right here. Right. Let's work one more. And I'm gonna show you something that looks a little goofy, but we may wait till combination. Yeah. We're fixing to throw the devil in the Ohm's law here after this assessment. Okay. Let's throw a little devil in it right now. Really not as hard as you think. All right, so this is 10 ohms. This is 5 ohms. And this is 3 ohms. And this is 2 ohms. What do you think we have to do to even be able to solve the circuit?
Add R3, R4.
Yeah. Yeah. We'll go ahead and do that, and I really shouldn't have done this at this point. But when we get to combinations, this is where it's gonna start happening. We would add R3 and R4, and we would get 5 ohms. So I'm just gonna go ahead and call this R3 plus R4, right there. So, now that we've done that, we're back to just a parallel circuit, correct? Okay, so now, what is R total? Let's start there. I'll give you a minute to work. What is R total? Got 2 minutes, so my clock turns to 10:40. Got a 10, and a 5, and a 5, parallel. It's gonna be less than what?
5.
It's gonna be less than 5. It may be less than 1, but it's definitely gonna be less than 5. I can't tell you the is, but I can tell you the possibility. How about doing the math? All right. What'd y'all get? 2. Wow.
I got 2.
I did not intend to do that on purpose, but I'm glad I made it a nice even number. So let's try it. 1 over RT equals 1 over 10 plus 1 over 5 plus 1 over 5, common denominator.
10. Is that
I don't know if they're fixing to bring the building down, I hope they inform us first. Under 5, too long. Yeah, that worked out. I did it on purpose. It is 2 ohms. We'll just leave it a simple parallel, we won't worry about that other, well, we might, we'll see.
Did you just get through? Did I work it?
All right, yeah, we'll make everybody else close their ears when we get that one. It's actually pretty easy when you get down to it. All right, so we know RT, so what can we get right away? I total. I total is equal to 5 volts divided by 2 ohms, which is equal to what? 2.5 amps. So we know we got 2.5 before we get to our branches and after coming back from our branches. So let's get I bar 1, I bar 2, I bar 3. Alright, so we've got 5 volts across R1 divided by 10 ohms. So what is the current through R1? 0.5 amps. Alright, here we have 5 volts divided by 5 ohms. 1 amp. And that's the same as R3, right? 1 amp plus 1 amp plus half an amp equals 2.5 amps. That's our total current. So that proves out right. For those of you that's interested, back here we had R3 and R4, right?
We just treat it like a series circuit on its own, right?
What was R3? Which one was R3? The 2 or 3?
R3 was 3 and R4 was 2.
Okay. R3 was 3. R4 was 2. What's the current through this branch?
1.5.
Nope.
2.5.
Nope. What is the current through this branch? 1 amp.
Yeah, that's what I'm about to say.
So if I've got 1 amp of current flowing through this guy, what is my voltage drop across R3? Yep, it's gonna be, voltage is I times R, 3 times 1 equals 3 volts. I times R, 2 volts. 3 and 2 equals applied voltage.
Current will just be split between the two.
Well, no, they both see the same current.
Yeah, that's what I'm saying.
Yeah.
Like yeah.
Right. But the voltage would be split between 2 of them. Exactly.
2.5?
I did it right, I just did the math.
Huh? What is that question?
Yes. What are y'all's questions? Do we want to come back and work some
What time is lunch?
problems, or
I
do we
did not break that.
want to come back and assess? Raise your hand if you want to assess after break.
What happened?
All right, 5 till, come back. I'll have the password. Let me make sure Mr. Lee and them are ready to assess. We'll be all. But come back at 5 till either way.
Yeah, you should have just said that, man. That's what I could bring speed up when we're talking about.
Wait.
Basically, that was going into the whole conference.
Yeah, 'cause he said I think it was all
Oh,
three.
it's gonna break my mind.
Imagine if you get to the point where it's three.
Hey,
Because, you know, the
hey, baby,
current
you talked
is
about,
one.
what you talking
So
about?
with that, you have to.
He was working.
The resistance form is usable.
I'ma tell Connie.
Please.
I'ma tell it. You know I'ma tell it. So he can get a whooping.
Yeah, he needs it.
You gotta do see that.
They voted from over there, that was,
It's like, it actually dips in there, it's like, it's significantly jacked up. I'm like, cause there's no meat right, you know, on the side, I'm like, there's no meat, and it goes right on the line.
Going back to the original
I was sitting in the, when I did it, I was sitting there, and I was sick. I was like, I'm not trying to be a little bit extra, this hurts.
I bet you.
I got so bored of doing, ridiculous pickup lines. I mean, there was some good.
Last night.
No, like 5 minutes ago. I was so bored, I've been over there looking up ridiculous, pickup lines or something, no cracking up.
I'm finna whoop you.
Hold on.
What was
Watch
it?
out.
It's like, what is wrong with
It was hilarious today.
It's okay.
Y'all have fun, you hear?
Thank you. Stop pick me up sometime. Pick me up.
Livingston, how's it going?
How you doing? All right.
You got Tony working today?
Yeah, you got them on top of that. Got them on top. Appreciate that. Got come back, we brought, appreciate it. How are you? How you doing?
Yeah, I know what it is.
What are you doing?
My kids is great.
I
My
did the same way I did it.
kids is great kids.
You did the reciprocal thing?
I'm good on the Macy's. He real good with the Macy's.
He put my name in when I first moved in. I've been in there about 20 years.
Yeah, no problem with that.
Well, it's told. But it been 20 years. since I had
Oh,
my
yeah,
child.
oh, yeah, oh, yeah.
What's the total business?
But it been told.
That long?
Hey, guess what? The summer gone, so it's all right.
Oh, yeah.
Put a little, well, right now it's cool
That's
to
the entire service.
everybody
That's
in
the
the
entire
house. I don't
service.
understand.
Just that last,
It's crazy.
very last break.
But my house cold anyway, by so many trees.
What is the total?
Oh, you got you.
It's automatic.
Yeah, it's in the sitting side, that side.
Never did that first one.
I don't teaching, I'm serious. I cannot understand. I get something, then you jump to something else.
That's your current.
And it throw me off, so I just say, I'll wait till I get home.
Would you watch the video?
No, I look it up and figure it out myself. I can't understand.
You see what I mean with the three,
See, like right now, I'm lost. I try to, listen, but I can't.
These two, this one's positive, here, here.
How much do you know?
That's the next step, that's the next step. It's gonna be serious.
I know it will work, cause
Yeah, it's
you
gonna
know,
be
it's, you know, if I go there, if I take a time here, and I look at my numbers and I'm like, I know the background of it, I just don't.
That's a nice test.
They gonna have no competition.
Sit down and say, I'm fine.
It's so proud.
It's through. That's me.
Yeah. I like the one specifically.
What if I go there with you?
Oh, that's what I was gonna say. There's one that,
That's something like a couple months.
depending on how you read it from one side, it says love,
See how
the
that
other
goes.
side says love.
On the, just to make sure what I want. Get that. Honestly, that's it.
We're not gonna test though, because I did forget some troubleshooting stuff. So we're gonna do some more stuff, cause this may be on the test.
Oh, really?
And today it may be before the day's out, so I'm gonna have to. Well, let's talk about, let's just do a plain old parallel circuit.
Well, we're gonna test it anyway.
Absolutely not. Oh, you're going home, just not now.
I'm a little tired.
All right. What is our total? First one to give me the right answer
Can go home.
and go home when we're done.
What is the
Our total.
1.6. 1.6.
Gonna be less than 3. 1.6. 1.6 what? 4.
I get it going, right?
So obviously, we'll take the shortcut method, we'll pop that into our calculator rather than do all this common denominator stuff. We'll make sure we're right. So we'll say 3 reciprocal plus 6 reciprocal plus 9 reciprocal equals reciprocal 1.64. Yep, round it up, that's exactly right. So we're good there. So now, let's get I total. What is I total?
Seven point three.
7.31, right? 7.32, yep. I didn't round correctly. Alright, 7.32 amps. So all we did was we plugged in our calculator, we got our total, we did the Ohm's law for 12, for I, which is V over R, and we got 7.32 amps. So let's get I of R1, I of R2, I of R3. Well, divided by 3 equals 4 amps. 12 divided by 6 equals 2 amps. I can pretty well guess that one, but I'm gonna calculate it just to be sure. 12 divided by 9. It comes up 1.32. So we had a little rounding error. That's okay. We could go 1.33, we could stay 1.2. It's not gonna make a big, huge difference in the outcome. So, so either way, we come out with approximately 7.32, 7.33. Now let's talk about this. R2 opens. R2 is supposed to be a 6 ohm. what just happened to our circuit?
It just
Stays the
quit.
same, and the second one gets all current
Second,
Your total resistance changed, so.
Yes, it
therefore-
does.
first one gives us.
Very good. So we're gonna write our new R total in blue, close to here. What is our new R total?
2.25.
2.25 ohms. Here's what happens. We had a current path a while ago that would be through R1, and I realize now I don't have these labeled. R1, R2, and R3. So we had a current path going this way, a current path going this way, and a current path going this way. R2 open, so that leaves only 1 and 3 in parallel. So we got 3 in parallel with 9. Let's lay this down so I'm right on my calculator. So 3 reciprocal plus 9 reciprocal equals reciprocal 2.25. So that's our new current. So what is our new resistance? What is our new current? 5.33. We get that by dividing 12 by 7.32. No, 5 times 1. Right, sorry. 12 divided by 2.25, and that gives us 5.33. So now, what is the I of R1?
That's gonna stay the same.
What? It does, doesn't it? I want to see how long y'all doubt me. What is the I of R2? 0. That circuit is broken. It's no longer drawing any current. And what is the I of R3? Same. We still have the same voltage. We still have the same resistance. So current is going to be the same except for the branch that opened up. Now, does that logically make sense? If we have a light, a little bit brighter light, and we got something else that wouldn't pull a light, a fan, and all of a sudden we unplug that brighter light, this light's still going to draw the same amount of current. It's not going to suddenly see any greater current because it's seeing the same voltage. It is what it is, which is a 3 ohm load. This fan, it's not going to change. It's seeing the same voltage. It's not going to suddenly speed up. It's going to draw the same amount of current. So when we eliminate a branch, the other branches are still seeing the same voltage. Therefore, they're still going to draw the same current, but overall, we're going to draw less current. We're going to draw less whatever the branch that fell out was. So that's a good troubleshoot. What happens? Yep, overall resistance goes up, overall current goes down, which is just in line. Remember, an open is nothing more than just not powering a device when we're talking about parallel. We're eliminating power to a particular device or a particular load. What happens if one of those branches shorts? That's right. Here's what's going to happen. At least for a momentary moment in time, RT is going to be approximately equal to 0 ohms, and IT theoretically is going to be equal to infinity, or at least to the maximum current that the source can provide, and but then something's going to trip or something's going to blow up. So yeah, if we short one of those. All right, what else can we talk about as far as troubleshooting? All right, let's go back to R2 being open right here. R2 is opened up. we're gonna put a voltmeter in. I'm gonna put a voltmeter, not big ammeter, sorry. I'm gonna put a voltmeter here. And the other side's gonna go right here. What am I reading right there? How much?
12 volts.
12 volts, right. I'm gonna read 12 volts, and I'll place my meter right there. I'm gonna undo those leads. And I'll just use a red dot and a black dot after this. What about red dot here, black dot there? What am I gonna read? 12 volts. I've still got a path back to my source. This way. And this way. So I'm still gonna read 12 volts. Now that resistor is not dropping that 12 volts. The parallel branches are dropping that 12 volts, but we have a path back to our source. So, let's think about some things that we need to realize. If a resistor opens up, what happens to our overall circuit resistance? Goes up. We have more resistance, so therefore what happens to current? Goes down, because they are inversely proportional. Trying to think if there's anything else we can talk about as far as troubleshooting. After getting close to pretty much everything that would apply. All right, here we go.
How about a read?
We have an open there. What is overall current?
Nothing, 0.
0. We have lost any ability to source voltage to any of those resistors. We have no path from this resistor back to here, this resistor back to here, this resistor back to here. We have a path this way to each one of them, but it does no good without being a circuit. Yep, you have to be able to reach the circuit. What happens here if we have a break in a wire? Let's fill in some blanks. What is our total now?
What's the voltage on resistor 3?
What is the voltage? We'll get to that. What is the voltage across R1? What is I total? Here's what's neat. Look at there. IR1 was 4 amps, even if it was in parallel, even when we dropped 1, even when we dropped 2. So that holds true. Man, these symbols are killing me today, aren't they? Thank you. Yeah, we're back to a simple series circuit. Now, what were you asking, Cal?
What would voltage be on R3 then?
Let's see, if we measured, if we put a meter here, we put a meter here,
Read 0.
yeah, we'd be reading 0. Because we're not getting back to our source. That's pretty well it. Y'all could probably assess in 45 minutes if you want to try.
Yes.
Let me see if they're ready next door. Again, we have, I know y'all are.
That first thing on the morning test was good. Or you go to the hospital.
That's the end of that.
All right, morning.